Cool. So if you remember, last lesson, we were talking through this idea of differentiation. Differentiation. Actually, could somebody do me a favour? There's a heating control on the back there, just by the door. Could you just turn it off? It's a little bit warm in here. Just hit the big power button in the bottom right-hand corner. No, right. No, they're the lights. On the right, no, on the right. Let's do it. There's a big power button in the bottom right-hand corner. That's it. Good, excellent, thank you. Otherwise, we'll all fall asleep because it's too warm in here. Okay, good. So, what is differentiation? Who can remember? Perfect. Really good word. Really good phrase. Rate of change. Literally, how quickly does something change? Okay. Any other words that I kind of introduced to do with differentiation? Can people remember?
Gradient.
Perfect. Gradient. Rate of change literally just means find the gradient of something. Any other words? Tangent's a really good word as well. Okay. Okay, so it's all to do with finding the rate of change of something, but differentiation is more general than just dealing with straight lines. You can deal with any function, so even if it's non-linear, if it's like curves and things like that, you can still work out the rate of change. It's just the rate of change will be different depending which point you look at, okay? And if you remember, last lesson, I got to the point where I had this, okay? So how do we say this again? Can people remember? Yeah, dy by dx, literally how it looks, dy by dx, okay? And I came up with a formula. It was a first principles formula. Can anybody remember it? That's literally what this means, yeah. So it's to do with gradient, perfect, rise divided by run. It's just an infinitesimal change, a change which is really, really small, yeah? But it was this weird thing. So I said, okay, it's the limit as some quantity approaches 0. Now, what is h? Can anybody remember?
The distance between x.
Good, yeah, it's the distance between my two coordinates. Because the point is, I'm dealing with tangents because I'm dealing with curves. Okay, so if I draw myself a little curve, okay, I'm dealing with tangents to talk about the rate of change. But the trouble is with tangents that they only touch the curve once. But in order to work out a gradient, or the formal definition of a gradient, is it's a change in y divided by a change in x. So I need 2 points. So what I need to do is consider a point which is really, really close to it, and then think about rise divided by run. Okay? And the idea is that I want to make that distance as small as I can possibly get away with. So small that it's basically 0. Okay? Can anybody remember what came next? What fraction came next?
Limit h equals to 0,
Yep.
x plus h minus fx,
Yep.
or divided by h.
Perfect, well read. Okay, so so this is literally rise, difference in the f, so the function values, divided by the difference in the x, which I'm defining as h. Okay. Now I asked you for homework to go away and read those notes on the VLE. Did we do that? Okay, good. Now there is an example in there which talks about dealing with this. So I want to do the same thing. Okay, so I'm literally just going to reiterate what's in the notes. So hopefully some of you will have read this. Here we go. Let's suppose I give you the function which is y equals x squared. So I'm saying y is some function of x, okay, and my function is x squared. My function is x squared, okay. So it's a nonlinear function. I want to find the rate of change at x equals 2. In fact, let me change that. Let's go for x equals 3, because otherwise there's too many 2's going on, okay? So I want to find the rate of change of this function at the point when x equals 3. This is how I would do this. I'd use this idea. I know that the rate of change is just simply my gradient, my dy by dx, okay? So I just need to think about what I need on the right-hand side. Are you happy that I have f of x? F of x is just x squared. That's my function. So let me write that down. So I know that my function is just x squared. So I've got that piece of the puzzle on the right-hand side. But what else do I need? Well, h is just a value which approaches 0. So I can just consider it as a value which approaches 0. But are you happy? The other thing which I need is f of x plus h. Yeah? So what would f of x plus h be? Almost. You're literally taking x plus h. That's your input, and you're sticking it into your function, which is x squared. So you're literally squaring whatever you put in. So if I'm putting in x plus h, all I need to do is square it. That's my function. Okay, just squaring something. In fact, let's expand this out. What is this thing expanded out?
X squared plus
Plus h squared. Yeah, plus h squared. Okay, good. Okay. It's not just x squared plus h squared. Hopefully some of you can realise why. Okay, it's x squared plus 2xh plus h squared. So now I've got my two pieces which I need. I've got this piece and I've got this piece. I just need to stick it into my definition of my gradient, the definition of my rate of change. So okay, here we go. I say dy by dx will be equal to, okay? Well, it's going to be the limit as h approaches 0. I'm basically just saying here whatever h is, it's just got to be really, really small, okay? And then it's f of x plus h, which I've said is this thing here. So it's going to be f of x plus h, which is x squared plus 2xh plus h squared. Happy with that? Mm-hmm. And then I've got to take away f of x, which is just x squared. So I'm taking away x squared. And then I've got to divide through by h. Are you happy with that? I'm just sticking things in the puzzle, like pieces in the puzzle. Okay. All right, let's tidy this up a little bit. Okay, I'll just write my limit again because I'm not doing anything at the moment. Are you happy? I've got 2x squares that I subtract from each other. Okay. So in other words, I can just say this is going to be 2xh plus h squared all divided through by h. Okay? You happy now I can make cancellations? I'm just going to divide each of these terms on the numerator by h. So I'm going to cancel that one, and I'm going to cancel one of the h's there. So are you happy that what I'm left with is my limit as h approaches 0 of 2x plus h? You all happy with that? Okay. Now I've simplified as far as I can take it, what's left to do? Well, it's left to consider the limit, okay? I can't simplify my terms anymore, I can't simplify this anymore, so I'm left now to consider what my limit is doing. All this says is that h approaches a really, really small value. In other words, it behaves like 0. It never reaches 0, but it behaves like 0 the closer it gets. So 0 is just really, really small. So if I have 2x plus h, which term is going to disappear as h approaches 0?
h.
This one is just going to disappear. That's all a limit does. It just says, consider what happens as h gets really, really small. Well, if I have 2x plus h, this thing is going to get so small, it's going to basically disappear. In other words, this is just going to be left with 2x. Does that make sense? Yeah, does that make sense? So in other words, what I'm saying is that if I have the function x squared, the derivative of that function, in other words, the rate of change function, is going to be 2x.
So 2x is that line though, right? So
Good point. Good point. So you start off with something that looks like this, x squared. Okay. What does this literally say? What does this function literally say?
like it's a parabola.
Yeah, okay, so it's a parabola. But what it literally means is you give me an x value and I will find the corresponding y value. Okay? This is another function, isn't it? It literally says you give me an x value and I give you, in this case, the rate of change of that function. That makes sense. Because if you think about it, you're dead right. I know that y equals x squared looks like that, doesn't it? Now, are you happy that this means the rate of change? The rate of change of my function will be different depending at which point I look at. Like, have a look. Are you happy that the gradients of the tangents at different points are different? Okay? Gradient of the tangent over here is really negative. Gradient of the tangent over here is still negative, but it's less so. And the gradient of the tangent over here is now positive. And the gradient of the tangent over here is like really positive. Are you happy?
But the thing I got confused is like we say 2x is a line goes, it shouldn't go like this, but in here we said it goes like this, it goes like this.
Right, so don't get confused, okay? What I'm drawing in here is my tangent line, yeah? The way which I think of tangents, by the way, is it's almost like a roller coaster. My curve is a roller coaster. The x squared is a roller coaster. The tangents are like zombies on a roller coaster. So the rule is zombies have to have their arms outstretched in front of them. Okay, and imagine you go down this roller coaster, so my hand represents the direction of the zombie's arms. So down here, my zombie's arms are really pointed downwards. Over here, it kind of gradually changes. Yeah? So my hand represents the direction of the zombie's arms. And that's my tangent. Okay? But you're right. Okay? This is a straight line. But the straight line just represents the relationship between the gradients. Okay? So if I'm plotting this would be y, and this would be x. Now, if I plot immediately underneath it, so I try and match up the same x values, okay? Let's try and match up the same x values. What I'm going to plot here is not going to be y, it's going to be dy by dx, okay? So dy by dx. So let's have a think, okay? What I'm going to draw in red is the value of my gradient at each x value, okay? So this x value over here, let's start over here. Would you be happy it's really negative? Really negative. So I'm going to draw a value. So this x value, so try and match it up. This x value is going to be really negative. It's going to be down there somewhere. Okay? Then as I move to the right, are you happy it's still negative, but less so? Okay? So this x value is going to be still negative, but less so. All right? And then this one here, okay, it's still going to be negative, but less so again. And are you happy as I move to the right? It's going to get less negative, okay? Now let's think about what happens over here, okay? So over here, it's now positive. So my dy by dx is now positive. It's going to be about there, okay? And then likewise here, it's still going to be positive, but it's going to be more positive. And then over here, it's going to be positive, but now more positive. Can you see that what I'm tracing out here is a straight line? The line which I'm tracing out is 2x, okay? Now this represents the value of my gradient at every single point. Does that make sense to everyone? Yeah? But the point which I want to get across to people is this is a function, okay? It's still a function. In other words, it still has an x in, which means you need to tell me which x value you want to work out the gradient at, okay? Because at the moment, I'm just saying that all of my gradients are just changing linearly. Just changing in a straight line with gradient 2, okay? Which means you need to tell me which x value you want to work out the gradient at. Have I got the x value that I want to find? They've told me. They've told me they want the rate of change, the value of the gradient, at x equals 3. So all I need to do is stick x equals 3 into my gradient function. So if I know dy by dx is 2x, then at x equals 3, what's the value of my gradient? Absolutely. Does that make sense to everyone? Okay. If I wanted a different point, let's suppose, for example, they wanted at x equals 100. What's the value of my gradient at x equals 100? 200. If I wanted a different point, let's say, for example, at x equals negative 500. What's the value of my gradient at x equals negative 500? Negative 1000. Okay? So what this thing represents, really important, is it's the rate of change function. It says you give me the point which you want to work out, and I will tell you the value of my gradient at that point. Does that make sense to everyone?
So it's like for the you get one function for the gradient, but for each x point, we got like according gradient.
Exactly, because you can see that the gradient is different at different points. Yeah. In fact, this literally shows the relationship between the gradients at the different points. Okay. So this is a function which is kind of like, right, I'm ready, I'm set up, you need to give me the x value that you want me to find the gradient at, because it's different at different points. Does that make sense to everyone? Okay, good.